Consider the conversation between Bob, Ted, and Alice. Bob intends to inform Alice via Ted that Carol does not like carrots. From Bob's message, Ted understands that Carol dislikes carrots and conveys the message to Alice. Notice Alice did not receive the original message exactly as it is, but is still able to comprehend the intended meaning of Bob's message. This was possible because everyone involved knows who Carol is and what dislike means. And this is the type of communication I'm going to discuss here today, where we deal with the problem of conveying the semantics of the message rather than the exact message itself. Hi, I'm Q, and this is an introductory exploration of semantic communications and related system designs. The classical communication model proposed by Shannon in his seminal paper, A Mathematical Theory of Communication, does not consider the semantics of a message relevant. Instead, the model is primarily focused on reproducing the message exactly as it is from the source to the destination. The model aims to achieve efficient transmission and ideal reconstruction of a message by utilizing two key procedures, source and channel coding. With source coding, each message is assigned a unique bit sequence based on the amount of information in the message, which is measured by the notion of uncertainty. To perform the operation, the source coding block utilizes sampling, quantization, and data compression techniques. The channel coding block adds structured redundancies to the source coded bit sequence. These extra bits helps to combat the impact of the noisy channel that introduces error in the transmitted messages. At the receiver, the channel input is first resolved by performing error detection and correction at the channel decoder and then reconstructed at the source decoder. The classical model provides an elegant solution to the communication problem. However, the model cannot convey the semantics of a message. So I ask, why is it important to consider the semantics of a message for modern communication systems? It turns out that the next generation communication systems for AR/VR headsets, autonomous vehicles, IoT devices, or sensing technologies, all of them needs to perform goal-oriented communication, where the common goal of the source and destination is to accomplish a task together. Tasks such as image classification, advanced reasoning, emergency detection, and sensing. This task requires storing and transmitting significant amount of data frequently. And this is when semantic communication can extract the most necessary information, that is the semantic features of the data, to complete the tasks faster and in a meaningful way. However, to realize such goal-oriented communication, we have to redefine the communication problem at a broader level. And as it happens, just a year after Shannon's model, Weaver classified the communication problem into three levels. Essentially, it starts with the realization that any need for communication between the source and the destination typically stems from the common goal of accomplishing a task cooperatively. For task completion, the source first needs to understand the nature of the task and generate some meaning or context, perhaps a set of instructions that the receiver can follow. The source then conveys the semantics or context by constructing a message based on an agreed upon language between the source and destination receiver. The coded message is then transmitted over the physical channel to the receiver, leveraging the classical communication system setup. At the receiver, the intended meaning or context is decoded to accomplish the task and achieve the common goal. The three levels are classified as the level A, technical communication, level B, semantic communication, and level C, effective communication. Leveraging the three-level model, goal-oriented communication can be achieved by next-generation communication systems. Consider the case for dynamic spectrum sharing systems that requires the use of sensing technologies. It is observed that certain frequency bands are underutilized in radar or military applications and can be shared with commercial networks to optimize spectrum usage. However, to opportunistically access these underutilized spectrum bands, commercial networks need to confirm if the bands are occupied and ensure they can vacate the band the moment the primary network starts operating. These networks do not have the means to communicate with each other to facilitate such dynamic spectrum sharing. As such, spectrum sensing or monitoring can be leveraged by secondary networks to observe spectrum utilization rate of the desired frequency bands. These spectrum monitoring units, SMUs, can be standalone units, transmitting the observed data to the secondary network via wireless transmissions, or they can be integrated sensing units. From the observed data, commercial networks can decide the band's availability by detecting the energy or power, S, of the signals against a predefined threshold. If the detected energy is above the threshold, primary network is occupying the band and therefore shared access cannot be authorized. To keep these secondary networks informed, the SMUs have to transmit the monitored spectrum utilization data at regular intervals. Typically, for a small observation window, the SMUs collect significant amount of sensing data, and even with data compression, sharing the observed data with the commercial networks is a challenge. However, the semantic features of the spectrum utilization data will have all the necessary information about the utilization pattern of our desired frequency bands and can also be encoded into a low-dimensional representation by a semantic encoder. In turn, only this code needs to be transmitted over the noisy channel and can be utilized by the semantic decoder to generate or forecast spectrum occupancy of our desired frequency bands. So how can we design a dynamic spectrum sharing system that is able to extract the occupancy pattern of certain frequency bands by leveraging semantic communication? We start by building on the conventional blocks for digital communications and process the source data, which is the observed spectrum utilization data of n frequency bands collected by k SMUs over the t observation window. The source data S is fed into our semantic encoder F with learnable parameters theta. This encoder could consist of several downsampling and convolution layers that compresses our data S into T over L m-dimensional vectors, where L is the compression factor that can be tuned during training of the semantic source encoder-decoder network. At this stage, the output of the semantic encoder Z sub E is a low-dimensional representation of our data S, and to discretize this continuous latent representation, we could perform vector quantization by utilizing a codebook consisting of j m-dimensional code words. This codebook is also referred to as semantic embedding space in the literature. To choose the code word that best characterizes our continuous latent representation Z sub E, we perform a nearest neighbor estimate. That is, we choose the embedding or code that is closest to Z sub E and return the discrete latent space representation Z sub Q. Note, the codebook is accessible by both the source transmitter and destination receiver, making it a shared knowledge base. As such, instead of sharing T over L m-dimensional discrete latent representations, we could just share the index of the chosen coded word used for vector quantization. In doing so, we further reduce the size of the transmit data. Note, our original source data S with the dimension of T by K times N is significantly compressed to a sequence of code indices of dimension 1 by T over L, and contains only the semantic features of this spectrum utilization pattern. The sequence can then be processed using conventional channel coding and undergo modulation to be transmitted as complex symbols via the wireless channel to the receiver. At the receiver, the channel input is first demodulated and the sequence of code indices are recovered. The receiver then goes through the dequantization process by looking up the code book with the sequence of code indices and regenerates a discrete latent space representation of the semantic features, that is z hat sub q, which is then fed as input to the semantic decoder. The semantic decoder generates the reconstructed spectrum utilization data S hat. Note the reconstructed output can be the spectrum occupancy of the n number of bands for the T observation window, or it can forecast spectrum usage for T plus D observation window, where D denotes minutes, days, or months. The semantic decoder G with learnable parameters phi can consist of several upsampling and convolution layers. The intuition behind this design is that we want to learn the distribution that best models the spectrum occupancy pattern of our desired frequency bands and use that to reconstruct or forecast spectrum usage. Perhaps we can extend our design to conduct wireless transmission of varying source data, such as images, text, speech, or audio-video files. And maybe the system can be equipped with various learning strategies. Either based on a communication protocol or from experience, the source can choose the most effective way to model or encode the source data, and leverage a wide knowledge base to enable the semantic decoder at the destination to generate meaningful and accurate representations of the source data. Moreover, the channel coding blocks can also utilize, say, an attention-based encoder-decoder architecture, for example, to learn the optimal code length that best adapts to varying wireless channel conditions. In other words, an end-to-end adaptive communication system design that conveys the semantics of our messages efficiently and reliably. With a possible design in place, here are a few thoughts on future directions and steps. I have put together an example featured on MathWorks webpage. Essentially, the implementation demonstrates how deep learning-based semantic feature analysis of a spectrogram can be utilized to characterize the spectrum occupancy of radar and communication signals. The source code for the implementation can be downloaded from my GitHub account as well as MathWorks website titled Spectrum Sensing with Deep Learning to Classify Radar 5G and LTE Signals. However, the primary goal of the vector quantized semantic communications design presented earlier is not just to classify the signal waveforms in the spectrum utilization dataset, but also to come up with a technique that would allow a low-dimensional representation of the data that can be conveniently shared over a low-latency reliable wireless network. To that end, I will explore the challenges associated in training such a vector quantized semantic encoder-decoder architecture with a discrete codebook sitting in the middle, and perhaps discuss the intuition behind the discrete representation of our latent space. As long as we are at it, transformers with attention mechanism can be discussed as well to see how we can learn the temporal relations in our spectrum utilization dataset and use that to predict future spectrum occupancy. Before I wrap up, I wanted to reach out to anyone who's interested and put out a few questions that we could discuss. For instance, what is the best way to process the spectrum utilization dataset before it is fed as input to our semantic communications system designs? Dataset Z is presented as time series data, whereas dataset X is processed as spectrogram snapshots that are labeled with different classes of radar and communication signals. Moving on, based on the processed data, which design will most effectively be able to learn the spectrum occupancy pattern of our desired frequency bands? Please consider sharing your thoughts. I appreciate the time you put into this. Lastly, I wanted to feature a few of the related works that inspired this talk and the full list of the reviewed literature. Once again, please consider sharing your thoughts and feedback. Thank you for watching this video.